This chapter is on the electric field. We'll learn what the electric field is in just a moment. And our first module in this chapter, 21.1, is the description and origin of the electric field concept. Well, if we think about two charges, these two charges, Q1 and Q2, when people first started thinking about the fact that this one exerts a force on this one, the force goes across a vacuum, and there's nothing in between here. How does this particle reach across and touch this particle and exert a force on it? This is called action at a distance. And it was a difficult thing for people to accept. And so what people did was invent something really strange that made them feel more psychologically comfortable. Ironically, this thing turned out to be an intuition that was well grounded, as we'll see a little bit later. They said, okay, if this particle reaches out across space and exerts a force here, that's not possible. So what it must do is this particle here must exert an invisible field that permeates all of space, whether there's anything there or not. And so this particle's field goes throughout all of space. Now, here's a particle Q2 that finds itself in that field, and the field itself exerts the force on the particle Q2, not this particle. This particle creates a field, and we call this the electric field due to particle 1. And now we know that this electric field is going to push on this particle and exert a force. So how can we rewrite that? Well, we know what the force has got to end up being. The force that's going to end up describing this is the force that 1 exerts on 2, which is going to be equal to Ke Q1 Q2 R2 minus R1 vector, and I'm going to write this in the vector form that we just had it, divided by R2 minus R1 cubed. Now, if you don't want this vector form of the force, what we can do is we can say, okay, if you can remember which way this points, namely in the outward direction that Q1 is pushing towards, you could write it as, without the vector notation, is Ke Q1 Q2 over R2 minus R1 magnitude squared. And then you would have to remember that this exerts the force in this particular direction. Here the vectors take care of that automatically if you actually subtract that vector. Okay, since we know what the force is, what we can now do is do something very interesting. We can say we want to break this into two parts, the charge 2 and the field, the rest of the force that exerts it on charge 2. So I'm going to factor charge 2 out, right? That is Q2 times Ke Q1 R2 minus R1 divided by R2 minus R1 cubed. Remember, the cube, 1 power of this, takes care of this and makes this a unit vector. Otherwise, this would give you another power of the distance between them. Equivalent over here, if we didn't want to do the unit vectors, you could write it in a simpler form, Q2 times Ke Q1 Q2 over R2 minus R1 squared. And of course the difference is this unit vector, again like we had from the last module, R hat, which is R2 minus R1 as a vector divided by the magnitude of R2 minus R1. So all we've done here is we've multiplied by this unit vector in order to point the right direction. Here's a simpler form of that equation. And now what we do is we want to write that force as Q2 times the electric field at that point. This is the electric field at the point that 1 exerts on 2. This would be the force that 1 exerts on 2. And so you can see that we now have an equation for the electric field. The electric field is this part here. Not this Q2, we factored it out. This part here is the electric field that 1 exerts on 2. Or we could better say it, if we look at this equation here, this is the electric field at the point 2 due to a charge Q1. At the point 2 due to a charge Q1. So now we can write the electric field must be equal to KE due to a charge Q1. Q1, let's say on Q rather than Q2, it'd be Q1 times R minus R1, and I will just drop the 2 now, divided by R minus R1 cubed. And this is the electric field. Or if we wish, in this simpler form over here, without the vector, we can write it as KE Q1 over R minus R1 squared. And that would be the field at the point R1. This is, let's see, this is 1 on 2, 1 on 2, 2. Or the electric field at point 2 due to a charge at point 1. Due to a charge at point 1 that exerts it on point R. Or if you want to, you can put that 2 back in there, it doesn't matter. And so the electric field is KQ over R squared. Well, let me give you an example. That will make it a little bit simpler. That should help you a little bit. Let's suppose we had a charge at the origin. At the origin, that means we're looking at that what the R1 is going to be equal to 0. And if R1 is equal to 0, you can see that R1 is going to exert on 2. So now we're saying at the point 2, we just have R. So R1 is 0, so this vanishes. And this would be, the electric field would be equal to K Q1 over R squared. So if we go out here distance R, the electric field at this point is equal to KQ right back here over R squared. And it always points radially out, so it's in the direction of the radial unit vector. So that kind of simplifies it. So it's very easy to figure out what the electric field is here. And for example, the electric field out, let's say a distance 5 meters, due to a charge Q1, which might be, Q1 might be 3, would simply be equal to K, which is 9e to the 9th, Q1, which is 3, divided by the distance out, 5 squared. So we can take 5 times 5 is 25, divide that into 3 times 9, and multiply that by e to the 9th, and that would give us our electric field. Conversely, you can see from this equation right here, if we know the electric field somewhere at a given point, due to all of the system of other charges, we can simply multiply it by the charge that's at that point. So this could be the electric field due to charge 1 back here, pushing out here, but we could have another electric field due to another charge, another one due to another charge, add all those up. And all in all, when we add those up for all the charges, we can say the force at a given point on a charge Q is equal to Q times the electric field at that point. Or conversely, the electric field is defined at any point as the force on a charge Q at that point divided by Q, which is the same thing as saying what? It's the same thing as saying if Q is 1, it's the force on a unit charge. So if you wanted to find out right here at this point on the page what the electric field is, you can put a 1 Coulomb charge there and say, which way does the force point? If it's 6 newtons and points this way, then the electric field is 6. and it points that way. Of course, the units are there, newtons divided by coulombs. Now let me mention some things about the electric field. The electric field lines display the electric field. At first, this electric field was an imaginary concept, but it turned out to be a real thing. And that was proven that the electric field exists. Even if this other particle doesn't exist out here, this electric field does go out. Electric field lines can never cross. They begin at positive charges and end at negative charges. If I have a conducting object, here's a conductor here, that's some kind of metal, and if I put electrical charge on it, the electric charge for a conductor always tries to get as far away as possible from the other charge, so I'll go to the surface. So the surface will end up with a positive charge everywhere, and therefore the electric field will spew out, and it'll always be right there at the surface, perpendicular to the surface. Even though it can get kind of complicated, it always leaves the surface of a conductor in a perpendicular fashion. E is always going to be 0 inside a conducting material. E is 0 in here. E equals 0 inside, because otherwise it would take some of those electrons or protons and push them toward the sides, and therefore the electric field is always 0 inside if it's a conductor, and E outside a conductor is always perpendicular to the surface. And that's an interesting point. The charge always accumulates where the surface has a small radius of curvature, and when that surface curvature is the smallest, we have the greatest charge accumulation. So for example, in this particular case, you see this sharp kind of point here, we would have a ton of charge accumulating right here, so much that charge would probably spew out into space right here. This is the origin of what is called St. Elmo's fire on ships, where you had sharp objects and the charge in the ocean would come up the mast and go to some point here. And it's also, if you have a building and you put a lightning rod up here and connect it, of course, to the ground, as you have to, you ground that. The charge, when the ground becomes charged and lightning is imminent, will race over here and race up here and actually spew out into the air and discharge the ground. And that's one of the main purposes of a lightning rod, is to make the ground neutral around there by spewing charge into outer space. We'll talk later about being inside the parallel plate capacitor and how it's so uniform and how that can be used as a source of the electric field. The electric field of a charged spherical shell is always 0 inside the sphere. So if I take a conducting sphere and I look inside, E is going to be equal to 0 inside that sphere. And therefore, if I look at the charge on the surface, if I look at it from a distance, it turns out that if I look at the electric field due to a sphere going out in all directions, this behaves exactly as though all of this charge here is accumulated right there in the center. So I can treat a sphere as though all the charge is at the center, right up to this point here to the surface, and then inside the electric field vanishes. That same thing applies to a gravitational field, so that's a very important concept. This was module 21.1.